So let's get started. So the last time we were talking about the setting where you have vista realizability. And you have fixed horizon planning, constant number of actions, you do local planning. And the claim was that there exists a planner such that a suboptimal policy can be obtained, is obtained using this planner in polytime in d times h over delta to the power of a, and b, where b is a bound how big the parameter is under this realizability. And then later on, we discovered that actually this planner can do more and will do more. It will compete with any policy, any memorized policy, deterministic memorized policy for that matter, not stochastic, whose value function is realizable, and compete with the best of these. Why? Okay, so here was the interaction protocol. As we know, it's because the algorithm is this optimistic algorithm that keeps a set of hypotheses of like what would be a viable parameter vector, and it always chooses optimistically for the first stage the parameter vector, and after that, after this optimistic choice, it runs a bunch of tests. And the way I explain this is that, well, like they're basically the primary purpose of the test is to prove that the promised total value at this initial state is going to be met. So you run this test, rolling out, using the policy that is induced by this parameter choice, and you try to verify using these rollouts whether the value that you predicted is going to be incurred. So you do this using the simulator. The induced policy crucially is defined as the policy that makes the Bellman equations consistent. And here we got rid of the max and we introduced this product trick or technique. Trick is just a dirty word that allows us to later just claim that these tests cannot run forever. So for the testing, I was saying that you run these rollouts, and along the trajectories that you obtain, you verify the consistency of the Bellman equation, looking at the TD errors. And if consistency is met in every step, then you're going to be guaranteed that the value that you achieve with this policy is as high as the value that was predicted. But this was kind of like hanging out there in the air. So today I want to explain this a little bit better with more details. And we are also going to look into how can we prove that these tests cannot fail forever. So they fail once, they fail twice, they fail a number of times. Every time they fail, we are defining the hypothesis set. And it's to be able to say that the algorithm uses a poly number of queries in the required target accuracy to meet its target accuracy requirements. We need to argue that these tests cannot go on forever. Okay, so this was kind of hanging out there. I was alluding to that by using this tensorization trick, we are lifting everything to a linear space, and then we have linear tests, and the number of times linear tests can fail is limited. So altogether, like how many times can you detect inconsistencies with some set of linear equations for which you suppose you have a solution? Well, at most the number of dimensions included or involved. After this lifting into this higher dimensional space, the number of dimensions is d to the power of a, basically, and so that is going to govern the query complexity. And lo and behold, the query complexity really shows some dependence like that, which we don't like, but that's what we got, right? So I argue that for a equals 2, this is just quadratic in everything. So let's be happy with that case. Actually, we are not really happy. The big question is whether you could do better than this. I suspect not, but that's just a conjecture. So that's an open question. Okay. Anyway, so how do we argue about this algorithm in a more rigorous way? I left off the last time by saying, okay, we're gonna bring in Euler dimension and whatnot, but no one really knows what Euler dimensions are. So let's go after this today. So let's put in some date here so we know what's going on. So kind of today we want to finishing off the tensor plan analysis. Not going to show all the dirty details of this, like some concentration inequalities I'm going to leave out because they're just dirty calculations. We already know how to use union bounds and all that, combine a bunch of concentration inequalities. That's just standard. So I'm going to focus on the key aspects, which is, okay, how do we test? What is this argument that we can, by testing TD errors, like that the TD errors are small, from that we can conclude that the total reward is going to be as high as predicted. All right. So for this, imagine that you chose some parameter vector theta hat, okay, in your hypothesis set. This was the optimistic choice. And then you roll out with the policy. And we have this initial state. So S1 in the rollout is going to be this initial state. So S0 is the state where planning happens. State where we need the action. So this is where we care about the value, whether the value is going to be high. And then we roll out. So we choose this sequence of ST and AT using the simulator, such that the AT is always consistent and the ST just follows the transition dynamics of the underlying MDP. And you roll out with this. And from this, you get, so this goes on for 8 steps. So AT is consistent with theta hat, and ST plus 1 is just from the transition dynamics. And so if you do this, then you also get to observe the rewards, and these are the rewards. We want to know that the expected value of these rewards is is at least as high as what we think they should be. So that's like phi1. So at every stage we have these feature vectors. Phi1 at S naught transpose theta hat. So that's the predicted value. So I'm going to introduce this notation. This is going to be V1 at S naught. More generally, I'm going to use V of H of S to be, I'm fixing theta hat, so that's fixed here. It's just the predicted values, okay? So these are just the maybe I should use hat so that we see that these are based on this gas. So you want to see that the reward that we receive is at least this much, and we allow a little bit of lag. Okay. So that's like the data optimality. So you're shooting for an error of data. If you are within an error of data of what is the best possible, then you're happy. Remember that if we don't fail with these tests, then we chose the parameter vector optimistically, so it gives you a value that can only be higher than the best possible value. So having total reward very close to that also means that your total reward is going to be close to the best possible value. So that's the strength of this optimistic choice. And now, the argument is very simple, actually. So you can telescope because consistency means that the Bamon errors are 0. So that actually means that if you expand the right-hand side here, so this expected total sum of the rewards, then that's the same as the expected total sum of just telescoping of the TD errors. Right? It's because the reward at the first stage, well, we have these Bamon equations, right? So the Bamon equation is going to give, if we are really consistent, then it's going to give us that V hat of ST is equal to R of AT ST plus, and then we have to take the expected value with respect to the next state distribution and roll forward with the index. So this is just consistency, right? So if your parameter vector was indeed consistent, then this is what you get. And of course, this is the same because of our assumption on ST plus 1 that it is generated from the same MDP. And this is going to be the same as if I plug in here st plus 1. And I condition on everything. So I condition on, here I only need to condition on st and at. Implicitly, these expectations, everything, it's like for a fixed theta hat. So this is not random here. If you write out the full proof, and like you would condition on that too. But I hope this is clear. Okay. And so we know that if you take expectation of both sides, then the expectation of a conditional expectation is just the expectation. So it follows from consistency that, well, right. Okay, something is fishy here. Let's do this. We will write something there. So it follows from consistency that these expectations are 0. Sorry, it's right. So let's write rather what we want. So we want to argue that this is large. This is the same as we had of S1 because, well, S1 is equal to S0. And then we're going to introduce this expectation. So this is V hat of S1. And if you have consistency, then V hat of S1 is just equals to RA1 S1 plus V hat of 2 S2 in expectation. Okay. And now we play the same with V hat 2 S2. We roll forward with that. So what is V hat 2 of S2? Well, it's R is the reward, direction 2 and state 2, plus the value function at the next state in expectation. So this is equal to the next thing. And so on and so forth. Oops, sorry. And if you do this up to the very end, then you will get the sum of the rewards plus this dummy value function at stage h plus 1. And I should have said that that's, you just choose that to be 0 so that you can always write these equations. And someone asked the question. What was the question?
Oh, why was V1 S0 equal to V1 S1?
Because S1 is equal to S0 by choice. You're doing rollouts from S0.
Oh, right. Okay.
Okay. Yes, this here. Okay. So we see that consistency holds. If consistency holds, then it holds that the predicted value is the same as the sum of rewards on expectation. So that means that if we convince ourselves that in every step, consistency, that is this thing holds, then we also convince ourselves that the sum of rewards is large. In other words, so what I was attempting here is rewriting this in terms of just like going backwards here. Like this sum is equal to this. And there you can write that as, eventually it's gonna be right. So we want to write everything in terms of the gaps, the TD errors, because we may have some TD errors. We may not be able to check whether this equality holds. We can only check it up to a certain accuracy using our simulator. So therefore, we are going to introduce this, gaps or TD errors, which are like the delta at ST and AT and I don't know, T and theta hat. That is going to be the difference of the right-hand side minus difference of the left-hand side. Okay, so if you write, okay, so let's write it here. So this delta ST, AT, T, and theta hat, let it be this difference. Okay. Then what we were doing here is that we were expanding, and every time we said that this holds with an equality, well, this holds with an equality if these gaps are 0, right? Otherwise, we are introducing a little error, which is like the gap. So more generally, for a parameter vector theta hat, which may or may not be consistent, what you have is that V hat of S0, the same as V hat of S1, which is the expected value of V hat of S1. And now I guess it's really inconvenient to use this sign convention. So let's do it the other one. So so this delta is the negative of this term plus the other term. So it should be, V hat ST minus this other predicted thing. So then I can just write delta here. So after I wrote this delta, then that has the V hat 1 S1, but it has this negative term, so I have to add that back. So I add back RA1 S1 plus, and instead of this inner product, because we are under the effect of this expectation, I can again just write V hat of 2 and S2. So that's because of this. Okay. So we see that more generally, if we are not sure about consistency, then, like add and subtract, collect the terms. You collect this bunch of data terms. And so you end up with the same thing as before. You will have the sum of the rewards. But you also have the sum of the gaps. Oh, these sums go up to stage H. That's the planning horizon. Okay. And so this holds if we can roll out fully to the end with the policy. And so we have that we had one of S0, the value that we are granted is equal to the sum of the rewards. It's going to be high, and this is going to be at least as large. Oops. As the actual sum of the rewards minus delta. It's going to be large as long as we can guarantee that all of these deltas here this is 1. So this is smaller than delta over H. Then if you sum up all of these deltas, okay, so let's do it for I. For every index I between 1 and H, this holds. Of course, the sum of them is going to be at most delta. And so you guarantee that your value is at least as high as the rewards that you're going to see. And so that's good. So this is what you need to test then. So it's automatically guaranteed that if the errors are small, then you're guaranteed to see like your predictions are data correct of the total reward that you receive. So this is what we need to test. And now the question is, all right, how are we going to test this? Well, the problem is that, but we have solved already this problem, that we don't know whether this AI was indeed a consistent choice. So rather than testing this, what we can test is whether the product of all these gaps is small. And so we're going to test whether along the trajectory, not this AI, sorry, but like plug in an arbitrary A, whether this holds. So what if, like there are multiple actions which are consistent, like which one to choose? Yeah. And of course, if you can guarantee that this product is data over age times, and let's say this TD error, like what's the range of the TD error? So if you're doing things well, then the range of this TD error is like minus age to age. So in absolute value, the largest TD error that you should be seeing is at most age. And for at least one of the actions, we expect consistency. So that's what we're going to test. For the other actions, we don't know. Maybe the differences are going to be big. So for the other actions, we allow a difference of age. So this is what we're going to test for when we are designing our tests. Because if we are testing for this, that this product is small, then from this, it follows that if there is a consistent action, then for that, the gap is also going to be small. No, this is this enough? No, this is not good. I think you should test. Yeah, you have to test for this. Yeah, fortunately. Right. And no. I think this is too much. Should just be testing for this. Yeah, so if there exists an action which is consistent, then with sufficient measurements, this inequality is going to be satisfied. And in that case, for that action that you can choose at the expense of an additional union bound, you can find that action, then this inequality is going to hold too. So here we are just relaxing a little bit this testing requirement. And the reason we do this is because the next argument that is going to argue that this test cannot fail forever, it really requires this product form. Okay. So we're gonna stop this testing if we find some data SI, AI, TI. So that says we are in, okay, we are in phase I of the procedure. Okay, and in this phase, okay, we are going to test actually for star. So if we find encounter a state action and some stage, maybe this should be, this is just I. That this test fails, then we need to shrink the hypothesis space. And then this is only used for shrinking the hypothesis space. It's not used for testing. Okay, so here we're going to say that theta hat I plus 1 is going to be all the thetas for which okay, the previous tests do not fail, and the new test doesn't fail either. So, and here, since we are uncertain about whether this choice was a good choice or not, we include this product. And here we have to expand this by h to the power of h a minus 1. Okay, so this is how you shrink the hypothesis space. And then the question is, how long can this go on? Right. So let's see. So what do we have here? We can ask this question a little bit more abstractly. So we have this space X, which in our example is going to contain the data, right? So this is data, e.g. for us, this is like the state where the test can fail, and the index where the test can fail, like the stage of the decision process. So that's X. That's a huge space because we don't have any restriction on the number of states. We have this parameter vector space. So these are hypotheses. And we start with a big space. For us, this was just the ball of a certain radius, I don't know, B. So that was the initial hypothesis space. And then we have this discriminant function that gives for every pair of data point and hypothesis a discriminant value. And we are happy if this value is 0. And for us, this was just, you know, take some function of Si and I, map it to some d plus 1 to the power of a-dimensional space, and take the tensor product, like amend the parameter vector with this constant bias of 1, take the A4 tensor product of the resulting vector with itself, so that's like a G of theta, and this is or data of Si of I and theta. Okay. So there is this discriminant function. So this is the function I'm talking about. This takes this form. The last time we looked at this, right? That if you take these products, then you can lift them to a higher dimensional space and write them in the form of some function of the data. So this is like the f, which is a function of s, and a function of age, and that's like a high dimensional vector, and then there is this G of theta, and then the whole thing was just the inner product between f and G. Okay, so just a linear test on some nonlinear function of theta. Okay. So you have this discriminant function, and we are asking how long can it go on that or test keep failing. In a way, this is asking the following question: how long is the longest sequence of points x1, x2, and so on, xn in X, such that for every I between 1 and n, it holds that the discriminant on xi, so there it holds that there we came up with some hypothesis theta such that the discriminant tells us that things are bad. Oops, it should be greater than equal, greater equal. While the hypothesis was not picked in an arbitrary way, it was picked in such a way that it was consistent with the previously generated data, such that delta of xj of theta is smaller than equal to epsilon for all j up to I minus 1. If you have a sequence, and I'm just going to denote these sequences with this notation that x1n lower index, it's just a sequence in xn. If you have a sequence with these properties, then we call this an epsilon eluder sequence for the pair for delta, actually. So that delta kind of summarizes everything, right? So it has this domain of the x and the theta, and then we are asking like how long can this eluting process go if we every step we kind of choose the absolutely worst point that would maximize the length of this sequence. Can this go on forever, or is it going to stop? So for historical reasons, so people associate this with the theta, right? So the discriminant function can be defined in a bigger set and then a smaller set, and then okay, how rich is your theta? They talk about okay, what's the dimension of the Aleuter dimension of theta, this hypothesis space, but maybe it would be better to talk about, I don't know, the Aleuter length. Well, I don't know. Well, it's still theta. Okay, so if we would allow data to map larger sets, like different sets, then okay, like it's about theta as much as but anything else. Long story short, the Aleuter dimension, which we usually denote it by this, but I'm going to put the delta there because that discriminant function is really important of this parameter space. Theta is the maximum length such that there exists a sequence in X that is an epsilon Aleuter sequence for delta and theta. Okay, so it's just like saying that, well, okay, if this number is finite, we would be happy because then we would know that the process is going to stop. So in our case, we have this very specific discriminant function. We want to know, okay, how long can this thing go on that we generated a hypothesis which was consistent with everything else that we have seen before, including the most recent fairing test, and then we find another contradiction. How long can this go on? The answer to this is that, okay, take this discriminant function and just analyze how long this can go on. And so the discriminant function in our case takes a very convenient form. It is if we go back, it was just a linear function, this inner product between the f and the g. So that it's just a linear function. And if you think about the hypothesis space of the image space of the thetas, right? So that this tensorized space, you can directly ask questions about like how long can the process go on. If you have a bigger space, then the process can only go longer. So you might allow yourself to consider all possible A tensors, such that, you know, the norm, the underlying norm is bounded by something like b to the power of a, right? To norm of it. And then this f just takes values in this corresponding Euclidean space, whose dimension is again d plus 1 to the power of a, and just ask the question, so how long can this go on? So all in all, the question to answer is the following. if X is a subset of some Euclidean space, I don't know, D-dimensional, that's a different D, not the same D, but I like to recycle that. And then theta is this B-ball. So it's like, it's another ball, okay. It's D-dimensional too. So okay, let it be S ball, right? And okay, so maybe I make, so let's denote this by B2S. And then here, I also need some boundedness. So I'm gonna say, okay, this is in another ball of radius gamma. So S and gamma are fixed parameters. Okay. In our case, all the data is bounded, everything is bounded. So this gamma and S are going to be implied by the restrictions that we put on the features and on the rewards and the parameter vector. And it's all fine. They can be calculated as the function of those more basic parameters. And then we can ask the question about just this very simple discriminant, which is just taking in a product. Right? So that's like the linear discriminants. I hope you guys are not confused about it. I'm denoting everything by theta. So this is not the same theta. That D is not the same D. It's like in our example, this corresponds to the lifted theta, right? Okay, but here we want to abstractly ask the question, what is the LU dimension of this specific theta space? So that is the question. Right. Okay, good. Any questions? So the claim that I want to show is this proposition that says that the Euler dimension, the Euler dimension is specified at some scale, right? So the epsilon goes into the parameter. So epsilon is this positive number. So in our example, the epsilon would have been this. So that's our epsilon later on. This in here. All right, so the critical value for the discriminant, that's your epsilon. That's your measurement accuracy. And it's going to impact the dimension. And so the claim here is going to be that this is going to be big O of D and log gamma S divided by epsilon. Okay, where the big O is meant that, okay, if D gets big, gamma S gets big, epsilon gets small, and this is the order of the quantity. You can calculate the explicit constants. It's not like that. Some big constants would be hidden here. you can get a uniform bound. That's not an issue. It's just easier to remember that in big O, like this is how things work, but here the big O is benign. So how do we prove this? Well, this is asking a question about how long a sequence can go. And so we should study the properties of these sequences. So that makes sense, right? It's asking a question about how long, what is the length here L-Euler sequence. So let's just take an L-Euler sequence that has a certain length n, okay? So let x1n be an epsilon L-Euler sequence. We want to understand what's going on here. And so what do we know about this Euler sequence? Well, we know that if we fix any I, just using the definition, then we know that, first of all, well, there exists a theta, right? Theta I, in this set, hypothesis set, such that the discriminant gives you a high value. So you're surprised to see a large discriminant value for this parameter vector. So this is just inner product between xi and theta I. And at the same time, for all the earlier data points, the discriminant gives you a small value. Oops, sorry. Yeah, I'm going to square these things. That doesn't change anything. And of course, from this, it also follows that if I sum up all of these, yeah, no, okay, just leave it like that. All right. So this is what we know about this discriminant sequence. So how big can this value be right here? So we know that it's at least as large as epsilon, but can it be much larger? Well, it can only be as large as the largest value that we get if we consider all possible values of theta, such that this theta is consistent with all the previous data, and also this parameter vector cannot be big. Right. So xi is a specific element of this set. Sorry, theta I is a specific element, specific parameter vector that satisfies these constraints. So if I take the maximum of this expression over all possible such values, I can only get something bigger. We use the same argument again, and we're going to say that, well, I can make this value even bigger if I change the constraint set to something bigger. So what's that bigger thing? So instead of saying that for all of these values should be small, I'm going to demand that the sum should be small. So now can put back the expression for this. This is this can be written in a algebra. This form. Okay. And let's just call this matrix. This is a moment matrix x of I minus 1. Then I can further upper bound this by taking the max. And this can also be written as theta transpose theta smaller than or equal to s squared. And if I sum up these constraints, then I again get something bigger, right? So if I have that there is, if these two constraints are satisfied, then of course the constraint that that theta transpose xi minus 1 plus lambda I with an appropriate lambda is smaller than 2 epsilon squared is going to be satisfied as long as I satisfy that lambda theta 2 norm squared is smaller than epsilon squared, and the maximum value of 2 norm squared is s squared, so I'm going to choose lambda to be epsilon squared over s squared. So with this choice, I can compress these to this constraint. And I'm going to call this matrix VI. So that's just to write things in a more compact form. So now I have the maximum of this inner product subject to a quadratic constraint on theta, that this is more than or equal to 2 epsilon squared. And how do you solve this? So how can we get a value for this? Have anyone seen similar things before? So what if we just had 2 norms squared here? So what if this was just like this? And we wanted to maximize this inner product. Do we know the solution to that? So what if I said that this is not even 2 epsilon squared, it's just 1? So you're looking for the maximum of, and there is symmetry, so I can drop the absolute value. So you're looking at the maximum of, okay, well, like who cares about this index I? So just the inner product between some vector x and theta subject to the constraint that theta 2 squared is smaller than 1. How big is that? Whether you have a square there or not doesn't really matter. Yeah, like one idea is to choose theta equals x because that maximizes the alignment between theta and x, right? It's about alignment, like you're kind of on the unit ball and you want to align with x. The only problem is that, of course, this doesn't have a norm of 1, so we have to normalize it. Yes. Sorry, it's right. And so if you plug this in, then what do you get? Well, you get x transpose x divided by the 2 norm of x. That's 2 norm of x squared divided by 2 norm of x. That's just 2 norm of x. Right? So if this constraint took this very simple form, we would be okay. So can we transform the problem such that we have this very simple form? So how would you do that? So you want to split, right? Yeah, observe V in theta. So we want to split this VE into 2 so that it pairs up with theta, because we just want to see a 2 norm there, right? So we could say that, like, let V be VI minus 1. I don't know, maybe absorb the 2 epsilon squared constraint as well. And of course, like, okay, to observe, like, you have to take the square root of this matrix. It's a positive definite matrix, so we can do that. And if you do that, then the constraint indeed takes the form of 2 norm of V bounded by 1. And now, okay, so what is happening with the objective function that we are maximizing? Well, we can express theta from V, right? So we can solve for theta. So that becomes square root 2 epsilon times VI minus 1 minus 1/2 times V. And so we find that the previous problem is equivalent to solving square root 2 epsilon, and the inner product between xi transpose vi minus 1 inverse v absolute value and subject to the constraint that 2 norm of v is bounded by 1. And we know that the solution to this is just the norm of the vector that's standing here. So this is vi minus 1 inverse xi. That's the vector whose inner product we need to take with v. But of course, we have this extra square root 2 epsilon. So that can come out. And then take the norm, the 2 norm. Of this. Well, if you square it, then it's easier to see what's going on here. So you get xi transpose, and then vi minus 1, 1/2, and then again vi minus 1, 1/2, and xi. So this whole thing is just square root 2 epsilon, and this quadratic norm of xi measured in this moment matrix. Okay. So this is the value that you get. So altogether, we started by that, okay, epsilon is smaller than this value. And so summarizing everything, epsilon smaller than something, which is smaller than square root 2 epsilon, xi, vi minus 1 inverse. So altogether, what we conclude is that xi, vi minus 1 inverse squared has to be at least as large as 1/2. Okay. So if you take an Aleuder sequence, you can define these moment matrices with this regularized moment matrices, and you see that the Aleuder sequence has to satisfy that this value here is big for every index. Okay. By the way, have you seen something similar to this expression? Do you recall anything that you've seen before? What is that? Where have you seen this? Shimon is saying Giro, Macron is saying Phi Giro. Yeah, so which lecture was that? Like what theorem comes to mind about this? T-Fair-Wolfowitz, yes. So this comes up all the time in least squares. So this is the width of the confidence intervals that we have in least squares or uncertainty. So it's not really a surprise that it comes up here as well. I mean, like, we also kind of brought in the technology that leads to this. So how do we finish? So what we conclude is that if you take an Aleuder sequence, then every element of the sequence has to satisfy this inequality. And then now we want to say this cannot go on forever. So for this, we need some new technique, new innovation. And it is, and this technique is also ancient. Just comes from the way people analyze least squares. So basically, you have to look at the determinant of vi. And we're going to lower bound the determinant of vi, and we're going to upper bound the determinant of vi. And we'll see that the lower bound is going to grow pretty fast compared to the upper bound. So it cannot grow, like this process cannot continue. It can only continue until, you know, the lower bound crosses at one point the upper bound, and then that's the end. Like the sequence cannot be longer than the maximum value of I, for which the lower bound is still below the upper bound. So if you take the first value, that the lower bound of the determinant of VI is larger than the upper bound, then that's a critical value, and the sequence cannot be longer than that. The sequence cannot even take that value, right? Because for the allular sequence, you will have these lower bounds and upper bounds. So how does this work? Like for the upper bound, there is an inequality which is called the determinant trace inequality. That just says that the determinant of any, I guess, positive definite matrix. Well, for sure for that. Well, I think that maybe, I don't know, the eigenvalues. Yeah, let's say everything is real here. So let's be sure. Positive definite matrix. Is upper bounded by its trace divided by d to the power of d. How do I remember this? Well, this is just AMGM for matrices, and actually, as most AMGN, the easiest proof is with Jensen's inequality. It's kind of, you take the log, and then you notice some convexity with the logarithm function, and you notice that the determinant is the product of the eigenvalues, the trace is the sum of the eigenvalues, and then it's just Jensen's inequality in disguise. Okay, so that's the upper bound. And if you calculate the trace of VI, how big is that? Well, VI has two parts. It's lambda times the identity. Okay, where is VI? Okay, I write the definition of VI here because we're gonna need it. VI is xi plus lambda I. So the trace of this is just lambda times d, plus there is this moment matrix, which are these outer products. And the trace of each of the outer products in xi is just the 2 norms squared of the corresponding vectors. So the trace of the i's moment matrix is just I times the corresponding norms, and the norms were bounded by gamma, and so the norm squared is bounded by gamma squared. So this is upper bounded by, okay, this is upper bounded by this value to the power of d. So what's the lower bound? So for the lower bound, there is another useful thing, which is that if you have matrices where to the previous matrix you add one outer product, then the determinant of the new matrix is equal to the determinant of the previous matrix times 1 plus, and you have to take magically the expression that we were bounding. So that's an identity. And the way you prove it is just with the determinant identity that says that the determinant of products of matrices is the product of the determinants, and you just manipulate things, and then you get this identity. Just writing VI as products, well, you have to take the square root of VI minus 1 and then bring out from left side, right side to all this. Anyways, so we know that since xi is an allular sequence, this is at least, this guy here is at least 1/2. So this is lower bounded by the determinant of VI minus 1 times 3/2. And then you can continue this way, and you end up with the determinant of lambda I times, so that's like V0, and 3 half to the power of I. Okay, and so this is the determinant of this is of course lambda to the power of D. So putting everything together, you get that the determinant of Vi is sandwiched between these two quantities. And you can take the log or whatnot, and then you will see that if you take the log of both sides, then here you will have the main term is going to be I times log 3 half. And then here on the other side, you're going to have like D times log, I don't know, 1 plus I gamma squared over T. Right, so you also have this D log lambda, which is a small term. So what's the largest value? What's the largest I such that this inequality holds? We have seen this, right? Like here on the left-hand side, you have linear growth. Here you have logarithmic growth. You just have to solve the inequality. And the result that you get is roughly as if there was no I here. Oops, okay, that was a little bit aggressive. Yeah, so you kind of solve the equation like that, and then you have to add some log terms. And that's just algebra, so I won't do it here. So from this, you get that the maximum value of I is indeed of the order of O the log. And so the reason, okay, so where is S and epsilon? Well, the choice of lambda. So what was lambda? It's epsilon squared S squared. So that's hiding here. And this goes to the other side. And so that's the main term. Okay. And it just meets this other term. So that kind of finishes, right? So Connor was asking some question about this relaxation. Yeah. If you, I guess I should have done this earlier. So I should have said here that when you are demanding that you're shrinking the hypothesis space, you can actually sum up all of these errors for the previous steps. And you can set things in such a way that you're still not eliminating the optimal parameter vector. So it's actually a little bit more complicated than what I've shown in here. I think that there is actually a little gap. So the editor dimension, let's change the definition of the editor dimension such that this is not for all. This is for the sum. And then earlier, we're going to patch the proof so that it works with that. Yeah. So scratch that. Right. Interestingly, this editor dimension is also going to come up later when we are doing online learning. Then it's quite a common technique. Well, it's maybe not surprising. It's just a way of reasoning about these things. So one more thing that I wanted to say. So here, there was another little gap, which was that here I said that the discriminant takes values in minus h and plus h. For this, you may need to truncate things. So rather than taking just the inner product, you need to truncate these values to the minus h plus h interval. And then that raises the question whether this L-Uder dimension is still going to be the same. And luckily for us, it's going to be the same. So that's not going to change anything, but that requires an extra argument. It's basically the same analysis as before applies. Right. Are there any further questions? Maybe you can stop the recording, and if you have any questions either for this